Good afternoon, everyone, and thank you for coming. Welcome to the TU Delft and to the Project Sparrow Symposium of 2022. My name is Nathaniel Steenhuis, and I've had the privilege of serving as Project Sparrow's team manager for the past year. About an hour ago, we had a small evacuation of the building, so my apologies if we're a little bit shaken up by that. I promise, as the song said, we didn't start the fire. Yeah, so why are we here? About a year ago, we stood on this same stage, and at that time, Project Sparrow had just accomplished a remarkable feat. A prototype liquid rocket engine had been conceived, designed, manufactured, and successfully tested within the span of 1 year, which is an accomplishment not many people thought possible, but we did it. And in that same presentation, I also laid out to you our vision for year 2 of the project, that we were going to build upon this success, and that we were going to show that not only can our engine fire, but we can further develop it and show that our technology has orbital capabilities. But first, before I get too far into that, I think a few introductions are in place. I have already introduced myself, but I would also like to introduce you to Project Sparrow. Over the past 2 years, our family has become a very large family indeed, and we've grown to include 65 members from 25 different nationalities, 6 different faculties, so a truly diverse team. Now, some of these people, or many of them, have worked in the background and may not have been as visible to you all as some others. However, without their contributions and the time and effort that they have poured into this project, it would not have existed at all. Many of them worked part-time, so also completing their rigorous studies next to dedicating their time to the project. And some worked full-time, meaning they put their studies entirely aside for a year to completely focus on this project. Now, the question that may arise in you is, why as students would you spend hundreds and sometimes even thousands of hours working without the incentive of money, and in most cases study credits, to work on a project that is probably best suited for governments, or until very recently, large companies? And this is a question that we've also entertained a lot, because we think the why of our project is very important. It guides our decisions, it shapes our mission. So the question becomes, why build a rocket engine at all as students? Firstly, what we believe is that we want to be leaders and innovators in the student rocketry community. And through creating connections with industry professionals, like many of the people in this hall, and students from other student rocketry teams, we believe we can show what we are capable of as students all across the world while we were still in university. And we believe that this will inspire other people to follow in our footsteps, come up with their own innovations. And as such, we believe that we can expand access to space and as such democratize it for all. Secondly, one of the core tenets of Delft Aerospace Rocket Engineering as a whole is to give its members a unique hands-on experience with technology they would otherwise probably not have access to or be exposed to. And this access to this technology and the experiences gained, we believe, makes our engineers and everyone we interact with better leaders in the future, better engineers, more capable to give back to society on a deeper level. And finally, and maybe most importantly, we firmly believe as a team that any advances we make, when we push innovation, that creates a positive ripple effect on the rest of science and technology. When we put ourselves out there as humans, when we encounter the harsh environment of space, when we take on these grand technological challenges such as we are doing here, we force ourselves to innovate, to think outside the box and come up with new solutions. And this will lead to positive benefits. An example I personally very much like is a shock-absorbing system that was developed for NASA's space shuttle originally to be able to withstand the intense loads and forces of launch. This system and the technology it's based on is now in use across the globe in buildings that are vulnerable to earthquakes. And there, this technology is saving lives. So today, we will give you a bit of an insight on whether we accomplished our goals or not, and how we went about taking these grand ambitions and turning them into realizable goals. And to that, I would like to give over the word to my wonderful colleague Carmen, who has served as the Project Sparrow systems engineer this year.
Thank you, Nathaniel. So while Project Sparrow's main reason to exist is to form and train students before they enter the industry, we needed to have a mission that would define us as a technical engineering project. Let's start with some DARE's history. DARE was founded in 2001, and since its foundation, it has always had a flagship project. This has usually been the largest project that the society was undertaken, and it was also a symbol for the direction that the society wanted to go towards. For many years, this project has been Project Stratos. Project Stratos worked on combining the latest technology that DARE developed into large-scale, record-breaking rockets. This started with Stratos 1 in 2009, which was powered with a solid engine, and moved into Stratos 2, 3, and 4, who were powered by a hybrid engine. About 2 years ago, in summer 2020, we decided that we had already innovated a lot and understood a lot the technology of hybrid engines. And therefore, we decided to develop the first liquid engine. And that's where Project Sparrow was born. Let's take a step back. I mentioned that we decided to move from hybrid engines to liquid engines. What does this mean, and why did we decide to do this? Hybrid engines are engines where the fuel is solid and the oxidizer is liquid. This means, as you can see on the slide, that the fuel is actually part of the engine itself. Hybrid technology has served very well the purpose of Stratos 4. However, throughout the decades that we have been developing it, we have also encountered some of its disadvantages. For example, for the engine that you can see on the screen, which is a Nimbus engine of the Stratos 4 team, it took over 370 man-hours to manufacture it. That, to put into perspective, if it had to be manufactured by one person, it would take more than 2 weeks if that person would not sleep and would not take any breaks, just make an engine. So it sounds pretty inefficient, doesn't it? Well, it gets worse. All this work is to make one engine that you can use once. We were not able to achieve much reusability with hybrid technology. And this also poses a problem when developing an engine, because it can take up to months in between test and test. On the left, or on the right, you can see the analysis of a Nimbus engine after a test. And as you can see, we had to open the engine in two to be able to see the state and how it looked like. So you can pretty much not use it again. So Sparrow decided to move into liquid engines. Liquid engines are engines that run on liquid fuel and liquid oxidizer. This means that the combustion chamber is empty, and it is the place where both liquids meet and combust. Liquid systems are usually more complex than hybrid ones, but they also offer way higher performance and also a more versatile design. The most tricky aspect of designing a liquid engine is making sure that both liquids arrive to the chamber at the right time. But this advantage of liquid technology, it can actually be seen in industry. The majority of the rockets, of the commercial rockets out there, are powered by liquid engines. The main advantage that we found is that, as you can see on the right, that is the combustion chamber of the firebolt after a hot fire. There is no structural damage. The black marks that you see are just some combustion marks that you can just clean, but the engine can just be reused. And this means that the time between tests is very little, and you can learn a lot about the engine when you test it. So Sparrow was born with a mission to develop a technology demonstrator for an orbital rocket engine. We wanted to prove that as students, we can develop this very complex technology that is the standard in the industry. And we can do so with very limited experience and very limited resources. The students that started Project Sparrow actually had very, very ambitious design goals for the engine. They wanted to make a liquid engine that was cryogenic, that would have regenerative cooling, thrust vector control, and that could fire for up to 40 seconds. And of course, these are very ambitious goals, but they actually drove the students, motivated them to accomplish a lot during the first year. In just 1 year, by summer 2021, Project Sparrow accomplished its first milestone. For the first time, we ignited a liquid rocket engine. And this is a prototype, we call it the battleship, a prototype of the firebolt engine. So I want to show a video in which we can see this ignition, and we can also see the reaction of the team to a 1 year of work, of very hard work that led to this moment.
4, 3, 2, 1.
So very short, but very important. Based on this progress, we, as the new green team, took over in September 2021. Based on the progress of the previous year, we sat down and we decided on our goals for the academic year 2021-2022. We wanted to achieve a long duration of the firebolt engine, and at the same time, develop a reliable testing system and reliable operations that would allow us to test the engine enough to make a final version. And this combined would enable the project to move to the phase of rocket design in the next year. So these were our expectations, our ambitions, and we're really excited to start working on them. But then one major setback of the project happened. 1 day after the successful test that I just showed, there was an attempt to ignite the firebolt engine, which resulted in a failure. This was a very critical moment for the project and definitely a very hard hit for the team. We were quite green, we didn't understand how the system worked, and now we were presented with the challenge of figuring out what went wrong and being able to fix it. What's important to say is that we are developing a very, very complex technology, and that these kind of failures are always a possibility. What's important is to look at these failures as a step in the progress of the development, and not just a setback. I would like now to invite to stage Jan, Chief of the Propulsion Department, and Philip, Chief Engineer, that will talk about the challenges that we encountered during the project and how did we overcome them.
Thank you, Carmen. So at the tail end of the first year, we'd successfully ignited the prototype engine. This was, as Carmen mentioned, a gigantic step for the team. In this first year, big strides were made towards achieving our goals, towards demonstrating the feasibility of student liquid rocketry. But the system we developed was very much a pathfinder. It was already pushed to the limits of its current state, and fundamental improvements would be necessary to move the project further. But more immediately, we just had a major test failure with significant damage to hardware. We had to be able to explain why this happened, and we had to introduce solutions to address any issues we found. This for ourselves, but also to give assurances to various stakeholders. Conducting these tests is a privilege. The facilities are certainly not run-of-the-mill, and DARE, as a society, holds itself to a very high standard of safety. This challenge is one that would call for thoroughness to the extreme.
And we were facing this challenge as a completely fresh team. Not only did we not know how the system entirely worked, obviously, we also had no clue how to perform a technical investigation about its failure. From the get-go, we took great inspiration from how aircraft investigations are conducted. We took meticulous photographic evidence right after the test failure so that we had a lot of evidence to base our investigation off. Then, we decided to perform a root cause analysis. Root cause analysis is an industry standard method of conducting an investigation which helps discover all possible theories or possible reasons why a failure might have occurred and narrow down all of these into the ones that are the most likely to have actually caused the failure, the root causes. For example, if a rocket is to break up in flight, the investigator needs to ask a question such as, why could a rocket break up? The reasons could be sort of trivial but unlikely, like a bird strike, or the rocket becoming unstable and the structure failing. Taking it further, why would the rocket become unstable? For example, the separation system could fire prematurely, the parachute deploy, or the fins, which are the elements providing rocket with stability in flight, could break off. This process needs to be taken for all possible branches until all viable theories are exhausted. Then, as many of these as possible need to be disproven, and then what is left needs to be improved. We did exactly that for our failure. It came up with a tree of around this size. We spent a huge number of hours trying to disprove and test as many theories as we could, and in the end, we were able to narrow it down to three main paths that could have led to the engine failure.
One of the three root causes was a leak in the engine manifold. The manifold is the last step of our fuel and oxidizer before they are injected into the combustion chamber. What you have here is your fuel and oxidizer, ethanol and liquid oxygen, two highly reactive liquids in close proximity to each other. What likely occurred was a leak of ethanol into the liquid oxygen side of the manifold, mixing of the two propellants, and ignition of the mixture upon contact with a hot metal surface. This in the internal volume of the manifold would have resulted in detonation and damage consistent with what was observed after the failure. All of this, the failure as a result of detonation as a consequence of mixed propellants, and mixing as a consequence of a leak, pointed to one culprit. This small piece, a Teflon seal, should have kept the fuel and oxidizer separate, but failed in this function. This root cause, two others, and a host of smaller, actionable conclusions were the culmination of half a year's work investigating this failure. We had investigated 48 plausible hypotheses and confidently disproved 33 of them. The remaining 15 could be traced back to the three roots Philip just mentioned. To evaluate these hypotheses and in addressing their solutions, we often consulted with university professors and industry experts. This was an amazing learning opportunity for us, and it allowed us to implement solutions we could be confident in. It was also amazing, as an aspiring engineer, to observe the enthusiasm these professionals shared with us about our project. The investigation shaped our perspective on our system, and while the process was long and sometimes grueling, the insights gained were invaluable. We shared our final findings with stakeholders in February of 2022. Our findings were found to be convincing, and our solutions were accepted. Our first test campaign of the year, our first major test campaign, would be conducted there 2 months later.
Before we could get there, however, we still had the second issue to face. Although the system was clearly capable of performing a hotfire, as proven by the success at the end of the first year, that single successful test was preceded by 15 full days at the test site, preparing the system. At this pace, we would never reach our ambitious goals for this year. There were a number of things to improve. Firstly, data acquisition was poor and unreliable. While developing a complex system, such as a liquid-fueled rocket engine, data needs to be collected of high fidelity of all the technical parameters during the tests. The entire system was based heavily on legacy, unstandardized implementations, which made it hard to work with and unreliable. One symptom of that was, for example, the liquid oxygen feed system, which was very prone to leaks. And leaks in a rocket feed system are not something to be taken lightly. We cannot just load up more propellant and go ahead with the test. That is because a liquid oxygen leak looks like this. Not only can it be dangerous, because liquid oxygen likes to make other substances burn, that's why we use it in a rocket engine. It also means that the system is unable to reach operational pressures. And the main reasons why this is so difficult to fix are twofold. First of all, liquid oxygen is a cryogenic liquid. That means it is stored at around 200 degrees Celsius. At those temperatures, parts change shape, changing the tolerances, making leaks more likely to occur, but also material properties change. Rubber, known for its flexibility and commonly used for sealing, becomes brittle and shatters. Secondly, our system needs to withstand relatively high pressures. 80 bar is equivalent to 800 meters under the sea. To put that in human scale, that would be the pressure felt, roughly, if one were to hold a Cessna Citation business jet in just the palm of his hand. And with all those challenges, we needed to be able to control the system down to millisecond precision and record data in multi-kilohertz frequency.
We took a similar approach to all aspects of the system. We researched numerous possible solutions, and once a direction was set, we conducted our first tests. These were small in scale initially, and conducted mostly from the comfort of the faculty, or otherwise a small field, just adjacent. We gained experience in conducting these tests, wrote our first sets of procedures, and reflected critically on the results. These unit tests built up our faith in the parts of the bigger whole, and once we put them together, we would surely have produced a much more mature system. This integration was a challenge of its own, and even more daunting were the ensuing validation tests. Validation tests of the whole complete system. To discuss these, I'd like to invite to the stage Lucas Hofmann, Chief of Feed and Pressurization.
So now that we talked a lot about these challenges we faced in the first half of our year, I want to dive a little bit more in how we went from design to testing to chasing our goals, which was mostly the case in the second half. And before we dive into that, I want to explain a little bit about the two major types of tests we conduct with the full team. Namely, we have a cold flow test and we have a hot fire test. And these cold flow tests, that's the image you see on top, is a component that is the fuel injection element. It's located inside of a rocket engine. And during these tests, we expel our propellants over this element and gain really valuable insights in how these components are performing. But we skip out on these risks because we don't ignite our flow, and it's much easier to work with. The second kind of test, the hot fire test, it gives these really pretty images. But for us, most importantly, we get some good validation data of how our engine is performing. So that's how we started out in December. Our first cold flow campaign, we did this one in Delft on a small test site. It was the first campaign we were performing with the full team. It was right before the Christmas break. It was really cold outside. We were out for 2 days, and we were leak testing our system, and we used this leak detection spray for this. But it was cold enough that our spray would just freeze up to our tubing, so we had to use a hairdryer to get the ice off before we could work on the system again. But we worked through it. We had some new elements on our system mounted, because we had all these technical departments working over the last months on their individual components. But this is actually the first time you get to see all these components working together, and you have to work as a team to make it work. Because if one of your things is not working, this whole test is not happening. And we learned how to work together, and we got some good data out of it. And with that experience we went out again in February, this time for a second cold flow campaign. We went out 3 days. The weather was again not the best. This time we had rain. But we got some good data here. We had a lot more systems redesigned already, so we could get a lot more insight in how our system that we want to use later in the year will perform. And yeah, this was already a really good learning experience for us, because on these kind of tests, not all your components will be working with you. So there will always be things happening that are out of your control. And you learn from these kind of tests that how to get the most out of the hardware you're working with. And with that mindset, we got some really good data on our fuel injection element, and we were really well prepared for the tests that were later to come that year. So that's when we started looking for our first hot fire. We had set up our systems. We had prepared our systems for these cold flows, but we wanted to validate that these systems actually work all up to spec. And that we wanted to do through another hot fire on our battleship prototype engine. And this is the same thing we did 1 year ago already with the old system. But now that we did all this redesign, it's really important that we show that these redesigns are functioning properly before we go to this higher risk test with the firebolt. And so we started out preparing. And one of these things you do during preparations is you take your whole feed system apart again, and you have to clean it, because we're going to work with liquid oxygen. So everything has to be properly cleaned. And we started running a lot of system tests, because the preparation will actually determine what's going to happen at your hot fire campaign. At your campaign, you have very little time to run all your tests. So the better you prepare, the more you focus on your details here, the smoother your hot fire campaign is going to go, and the further you're going to get there. So that's what we did. We spent a lot of times a lot of hours in the lab together, and it was really nice to work together as a team here. And one of the big steps we take in this preparation is we do a dress rehearsal. And during the dress rehearsal, we go over procedures. This is sort of a step-by-step guidebook that we write that lists all the steps we have to take from assembly to the hot fire test. And for us, this is really important that we get our efficiency up, because all these steps we're going to do at the test site are already listed out. But most importantly, we can make sure that it happens safely, because these procedures are written in a way that we come up with every scenario that could happen, every system state that we could end up in, that we write out a plan of what are we doing. And this is really essential for our test crew. So on this picture here, you see your test crew together practicing these procedures. This is again a moment where all our departments come together, and you have to work together as a full team. And by April, we were ready for our first campaign. That's where we headed out to our test site. We packed up all our stuff, and we started setting up our system. And this was also the first time we were working with liquid oxygen and ethanol. We went through a lot of safety reviews and system checks to make sure that our system is actually working up to spec, because liquid oxygen, it has serious hazards. So we had to approach this professionally, and we had to make sure every component was working up to spec. But after 3 days of setting up our system, we were ready to test. we have our battleship mounted on this picture, our battleship prototype engine. And this campaign really showed us that all the prep work we put in, all that efforts to look in the details, helped us with speeding up a lot. And so we wanted to go for 3 cold flow tests first to gather some more information about our system before we'd go for a hot fire. And we did our cold flow tests, and then on Friday morning in April, we got the first chance to do a hot fire test on our battleship engine with the new team, with the new setup, and this is how it went. We had a really successful hot fire. This was the first time that we showed that our new system is capable of boosting up, firing up this engine, igniting it. And this was a really big milestone in the project. We showed with this engine that we could produce enough thrust to lift up a small car. And as you saw in the background, there was still some blast shielding falling. There were things that needed to be fixed. But we were on the right track to get to our bigger challenges. And one of the things we also showed at this campaign is it took us about 4 days to get our system ready to get this hot fire in. And what Carmen told about us before, that we needed 15 days to get the system ready for our first hot fire. This was already a really big improvement and would really help us later on in the year. But it was still April, and our year was far from over. We had a lot more time. And we got really ambitious after this, because these kind of campaigns really give you the feeling that with this team, any big challenge, you can face it together and you can get through it and you can solve it. So that's when we started looking again into firebolt. We had this big investigation performed earlier in the year and we had our recommendations, but now it was time to actually put that to the test. And so we got into our preparations. We got ourselves a new engine. We started manufacturing smaller things we needed for a setup, because there were a lot of small things we wanted to tune and adjust to improve the system, make it more reliable, and get it ready for the big test. And so by July, we had a test plan ready. We are sitting together here in the room briefing the team. The team members were all going to be at the test site. Because this time around, the test plan was so ambitious that we would challenge the team in a way we haven't experienced before. Because on our last campaign, on our first campaign of this year, we did 4 explosions. But to get to this hot fire of a firebolt engine, we needed to do 8 explosions and a hot fire test. So that would mean we would drastically need to increase the speed of our tests, and that we have to get the efficiency up while still testing safely. And so we started out on our campaign. We had 2 days, we needed 2 days to set up our system, and this went actually really smoothly. We had one setback on the second day with a component failing, but with the right mindset, we were able to fix it on the same day. And on the 3rd day, we were ready to test. So during this campaign, we started out again with a test on our battleship engine. And this time around, we put the more expensive camera in the room. As we got some more confidence in our system, we took some really nice pictures of this hot fire. And we did this battleship engine test again because the battleship is really nice for research on, for example, our ignition sequence and how close we can hit our engine performance targets. This engine would melt down if we would burn it longer for 2 seconds. But the safety factors are a lot higher because this is basically a steel tube. This has actually been passed around on the Symposium last year, and we refired that same engine again. But after getting all that data in, it was time on Thursday to mount up our firebolt engine. And the team got really excited here because this was the first time we were going to do a hot fire test and cold flow test again with our firebolt. And so we set up the system. And we did some cold flow tests with it. In total, we did 3 tests. We were running through all our time on Thursday. And we had one more window on Friday morning, one more testing window to do one more test on this engine. And so we did our data analysis on Thursday evening. And on Friday morning, we had a hardware team setting up the engine again. We had the test crew filling up the propellants, and we had a data analysis team fine-tuning our test parameters. And suddenly we were there again, that point, the decision point, where the team was 1 year ago, before this whole investigation, are deciding, are we going again for a hot fire or not with this engine? So we had this meeting with the team. The goal was here to demonstrate that we can successfully start up this engine. We would only fire it up for full flow for 1.1 second. But this time we were way more prepared. We had this investigation done, we had all these recommendations implemented, and we had a lot more knowledge gained about the system from all these small tests we conducted at this campaign. So we decided we go for it. We had to push for it. We had to make this push for innovation. And yeah, the next hour, the test crew was getting the system ready for hot fire. And that was by far the most nerve-wracking hour of the full year. But we went for it, and this is what happened. We had a successful hot fire of our firebolt engine, starting it up for 1.1 second. And this was a really big milestone. This was the first time we were able, with Dare, to start up an engine, regeneratively cooled, 3D printed and liquid fueled. And with this test, we opened up a huge window of opportunity for a whole set of new research on these kind of engines, but also this showed how much potential these kind of engines have for the future of Dare. And we wanted to chase that. We wanted to go for those bigger milestones, because this project was not over. This test campaign was in July, but we're still having a bit of time. So that's how we organized another testing campaign. And this testing campaign was conducted 4 weeks ago from today. It was our final one from our team. And we went back for more. This engine is designed to burn for long durations. It is cooling itself during the burn. So in theory, you could burn indefinitely with it. But sadly, we have tanks that are limited, so we cannot go for too long. But we wanted to go for more. And we set up our system 4 weeks ago, and we hot fired again, and again, and again. And with the same engine, we showed that we're capable of firing it up for long durations. We went up to 15 seconds with this engine. We showed that cooling over our cooling channels in the walls of this engine work. It's about the inner wall thickness of this chamber is about, well, the thickness of a fingernail. And it's able to carry away over that thickness the heat, the immense heat of your combustion, and transfer it through these cooling channels away. And what even I think is more impressive is that this same engine we fired up 4 times now, reaching a total of 30 seconds on full propellant flow, and we did minimal refurbishments in between. And that's really where this liquid fuel technology is showing its potential. And with these tests, we started outperforming our test setup. We ran to the limits on what we can do with our current tanks. And this is us. This is the full-time team from this year. There were, as Nathaniel already mentioned, there are a lot more people who helped to make this work. We have a lot of part-timers who also helped us. But this is the story of how we got here. And yeah, this is a setup that is all student developed. We were able to create a test bed that can run these kind of rocket engine tests. And we were able, with a student team, to develop an engine this complex that can that can meet our design parameters. And with that said, I want to hand over back again to Nathaniel.
Thank you, Lucas. That's so great to see, even after they've seen those videos hundreds of times now. Yeah, so I wanted to recap a little bit what we've seen over the past 45 minutes and how far the project has come over the past 2 years. We have gone from a dream to a design to a prototype to an actually fully functional rocket engine over the span of 2 years. We have shown that we are capable as technologically, but also as engineers, to take on this challenge and probably even larger challenges. We have gotten 30 seconds of continuous hot fire data. In total, it's in the hundreds of gigabytes, if I recall correctly. So we can very well characterize how our engine actually performs and contribute to the body of knowledge that the world has on liquid-fueled rocket engines. We have developed technologies that had not been seen in DARE before. For example, a turbomachinery system that might be used on later iterations of this engine. We have become quite key players, as I mentioned at the beginning of the presentation, inspiring many others. In fact, recently we heard back from the International Astronomical Congress recently in Paris that people there knew us, knew our name, and said that they were inspired by our engine. And most critically, as Lucas mentioned, we have outperformed our test setup. We cannot go much further in developing this engine with this current test setup because we're limited by the tank size we have, for example. So we have not even reached the full capabilities of this engine, and it is already performing so well. We have not even reached, not even gotten close to the maximum temperatures that it can withstand. So all of that is to say that we think that our engine is ready for its next step, and that our technology within DARE is ready for the next step. So to introduce that a little bit, we're going to show you a video. But first, I'd like to say that with this, Project Sparrow has concluded its mission. It's achieved its original mission goal that Carmen introduced. And as such, we are concluding the project. This is not the end of our journey, though. As you will see in the video, it is a small recap of what we have achieved over the past 2 years. And it also shows a glimpse of what the future of DARE is. I hope you enjoy.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
More than 1 year ago, we started with the ambition to develop a reusable liquid rocket engine with an amount of power not seen in the Netherlands in over 75 years.
We indeed had a successful hot fire of our battleship engine for 2 whole seconds.
So over the past summer, we have already spent a lot of time researching, learning, planning, and debating on how to move this project forward. We're developing firebolt to run on liquid oxygen and ethanol, making it the first engine of this type ever developed in the Netherlands. So we're now getting ready for a hot fire, which means that we will actually put an igniter in our engine and we'll simulate how it would look if it were on a rocket and when it would actually fire.
4, 3, 2.
And with that, I'd like to hand over to the team manager of the brand new Stratos 5 project, Luke.
Good evening, ladies and gentlemen. I hope you've thoroughly enjoyed watching the journey of Project Sparrow and all the breakthroughs and accomplishments this team has made throughout the past 2 years. As Nathaniel mentioned, my name is Luke Masmer, and I will be the team manager of Stratos 5. Stratos 5 will be the next step in Project Sparrow's evolution. We will take the engine development, all the testing campaigns, and we will compile this knowledge and build a new system around it. We will build a new rocket that is powered by this liquid cryogenic engine. So this is an exciting next step in our team's journey, and today I'd like to tell you a bit about what we plan to do and what the next steps are. So first of all, I'd like to say a bit about DARE and some of the previous Stratos projects. As Carbon mentioned before, DARE has produced quite a few large-scale rockets over the past few years, demonstrating various techniques and technologies. We've tried to narrow the gap between what people perceive large companies are able to do and what students are able to achieve. After over 20 years of experience, DARE has produced 4 major rocket projects. So here you see Stratos 1 through 4. And so Stratos 1 worked on solid rocket engines. They were a bunch of dedicated TU Delft students who wanted to push the boundaries of European rocketry. They flew to a height of 12.5 kilometers, achieving a new record within Europe. And they really set the standard for solid rocket motors within DARE. And they really set a base for technology and what was to come. Then we have Stratos 2. They worked on a new type of engine technology, which was hybrid rocket engines. This presented many advantages and many new technical challenges. So they went higher, they tried new technologies, and overall, they tried to push the boundaries. Then we had Stratos 3 and 4, who worked further on this technology, developing one of the largest engines to date within DARE, the Nimbus, one of the most powerful ones yet. And they improved various other subsystems and made immense leaps in technology. So, because I know we've talked a lot about the engine so far and Project Sparrow, but I'd also like to show you some of the scale of what flagship rocket projects within DARE look like. So, I mean, flagship rocket projects within DARE have always been developed by large groups of students passionate about rocketry. They've wanted to make a difference, and they've wanted to experience building systems that typically aren't touched within their academic student lives. This is a photo from the Stratos 4 launch campaign, where you can see them integrating an electronics package into the top section of the rocket. With each flagship team having a seemingly more ambitious goal than the last, we continue to push the boundaries of what our team and what our students know is possible. This allows for the development of knowledge and skills crucial in the field of engineering. Here we have an example from Stratos 3. So this is the 3rd generation, and here we can see a launch tower integration. So most team members dedicate multiple years to these projects. Teams go through all sorts of environments, working together to solve unique challenges, giving real-world experience. Everything from design, manufacture, campaign logistics, and launch is all conducted by students. So here, this is back to Stratos 4 campaign. This is them setting up the launch tower, which was used in Stratos 2, or Stratos 3 and Stratos 4. So, and finally here, we have an example from Stratos 2. This is Stratos 2 Plus, which was the 2nd version of the rocket. This was the one that eventually launched. And so, from this, we can really see that it's a large logistical problem trying to launch a rocket. Many people are involved, many experiences and challenges that they need to go through, and it's a lot of work. So Stratos 5 hopes to continue pushing these advancements forward, and we want to utilize all the technical breakthroughs that we've gained in Project Sparrow. This engine really represents the next big technological leap within DARE when it comes to flagship rockets, having numerous advantages that will push our project forward. So after seeing the scale of these projects, I'd like to introduce more about what our defining features will be. So we are a team of 18 full-time students and over 40 part-timers. So there are three main things that I'd like to focus on. Firstly, like all DARE projects, we're a student-developed team. So we like to emphasize that and demonstrate that students can build extremely complex systems that are used basically by industry standard companies. Secondly, we want to be a technology demonstrator. We want to show that we can use and build extremely advanced systems, and we want to test new technology that's never been used on projects of this scale. Finally, we want to include some reusability in our new program. So we want to demonstrate the feasibility of a fully reusable rocket. So I think a lot of people may ask, why reusable? All the rockets in the past that we've developed have been single use cases. So in the industry, they're also typically seen as disposable vehicles. They're launched, they fulfill a mission, and then only a specific section is recovered. So there's a lot of time and effort that's gone into these complex structures, and it typically takes months, sometimes even years to finish. And so why would you throw away this? So with Stratos 5, we hope to change the norm. And this aspect of reusability will allow students to make incremental changes to systems, maybe propulsion, recovery, electronics. This helps with the development cycle, allowing new things to be implemented in the same vehicle. So even as industry shifts to developing new technologies that aid in a more reliable and sustainable future, we too want to undertake this challenge. So there's a few things that we can look at when talking about reusability for a launch vehicle. So far, Project Sparrow has already demonstrated reusability in the advanced propulsion system. So like Lucas said, they hot-fired the current print of the engine for 4 times. This was quite a milestone. Our next step would be to demonstrate reusability in multiple different systems of the rocket. Afterwards, we would plan to demonstrate full recoverability. So in previous Stratos missions, sections such as the nose cone have been recovered where data and electronics are handled. This is important because it gives viable data for understanding where the rocket went in a very extreme regime. So once we've done this, we also need to consider refurbishability. This is to ensure that all rocket systems from launch are safe. And then finally, we need to demonstrate that these systems that we've refurbished and we've checked are reusable again. So currently, we have a test setup for the engine like this. Like many people have seen this is the current Project Sparrow test setup. And so it is a test setup that is built for data measurement and ease of operations. Setting it up quickly and reliably is very important when we go on a test campaign, and we're not given a lot of time to do large, repeatable trials. So in order to accomplish our goal, we have to take this system and condense it. We need to weight optimize it. We need to consider the dimensions of such systems, all in an attempt to integrate them into a final rocket. So we must go to this, from this, to something that more looks like this. This is an exploded view of the previous Stratos 4 rocket. So the project is currently in its infancy, and we've already begun this fall. I hope you've enjoyed a little about hearing about the project and what the next step for the team is. We're all super excited and really want to show more. In the next coming months, we'll slowly announce more about the project, what our next steps are, and when you can expect to see things happen. So I would now like to pass back to Nathaniel, who will come back on stage and wrap up this symposium.
Thank you, Luke. Yeah, it makes me really excited to see that, well, our project, our little baby, is being carried forward into this new and exciting age for rocketry. I've already mentioned that we are concluding the project and evolving, but before we like to do that, there are a lot of thank yous in order. Because I mentioned at the beginning of the presentation that our family consists of 65 students, but that was not completely true. And there are actually a lot more people who contributed to this project. I'd very much like to thank university staff, the faculty, professors, and staff at the aircraft hall as well for contributing to this project. With your technical expertise and help in organizing, we would not have been able to do this. I would also like to thank the Dutch Royal Air Force for hosting us and being our amazing test site where we would have not been able to test without them. I'd also like to thank all of our sponsors whom have supported us with materials, with their technical expertise, financially. I'd like to thank our suppliers who have supplied us with amazing materials as well to complete our tests. And I'd also like to thank DARE as a society, because while we were only one team within DARE, I feel like everyone has contributed to this project. You have been very generous with your time and with your efforts in helping us succeed, reviewing our projects, helping us with the safety aspect, and it could have, again, not happened without you. And the final thank you goes out to our families and friends. I think I speak for everyone that undertaking such a project can at times be incredibly difficult, exhausting, and without your emotional support and knowing that you're there for us, we would not have been able to accomplish anything. So thank you. And now I'd like to invite all of our sponsors for a reception in the foyer. We have some snacks and drinks ready for you, and also a wide variety of setups of our hardware, where you can go up to the stands, read a little bit about them, touch them, ask our team members for good stories about them. So we look very much forward to chatting with you. And for the Project Sparrow members, part-time and full-time, I'd like to ask them onto the stage for a nice photo opportunity. Thank you.